Hey team, I'm going to introduce to you the unit circle now, which is the beginning of all trigonometry to come. So I know that's a pretty big statement, but this is going to be a brain bend. It's a longer video because there's a fair bit of stuff I've got to tell you. I was as succinct as I could be. If I do this in a math tutoring session, I spend a good hour on it, and then I might even come back to it another time. We'll probably have a few revises on the same thing. So yes, it's big, but it's super useful, and once you are fluent in it, you will find trig easy. You will be one of those kids getting 90% while everyone else is struggling to get 50 because you understand it and you get it well beyond just following the instruction set that is given to help you find things. So this video is the introduction, the theory behind how the unit circle questions work and a lot of the rules we use for trigonometry. And I have further videos that I'll make for putting it into practice. So hang in there, just do your best to wrap your head around it, and even if you have to go back a couple times, that's okay. This one is more difficult than some of the other stuff we do, so don't stress if it takes you a bit to get there. All right, and ask me questions, of course, because I can fill in whatever I've missed and make it as easy for you as I can. Ciao. This is the unit circle. It's a unit circle because it is 1 unit in radius, which makes my x value here 1, sits on the standard xy axis. My y value here 1, minus 1, minus 1. And it has the formula of x squared plus y squared equals 1. Now, before I go into the trigonometry side of things, let's just have a quick recap of the circle formula. Circle formula works because if I take a right angled triangle from any point on the circle and drop it down to the x-axis, I could extract that triangle and I could say that the x value was the width of the triangle because I went from there to there, and that would be the x value of that point. The y value would be the height of that point and the radius would be 1. Now, is that not the Pythagorean relationship for this? So you can see quite easily any point on the circle, even if we're over here, the y value will be positive, the x value will be negative, but I could still create myself a little triangle there. And if I put the x and the y, even with that triangle backwards with the negative x value, you square it, it becomes positive, the relationship will still come out at 1. So why am I talking about Pythagorean circles in a trigonometry lesson? It's because this circle is how we can track the ratios of sine and cos and tan for any angle, not just the ones inside our acute right angle triangles. All I need to do is put a theta into this triangle here, and that theta would obviously go here, and represent the angle of rotation of that point from this value here. So I'll call this value 0 degrees, and then I rotate around. And if I keep rotating around, that would be 90 degrees, 180, 270, 360, and so on. I could keep going round and round if I want. I could even go backwards. I could say 0 degrees, negative 90 degrees. So every point on the circle we consider to have an x and y value and now a theta. So the theta for this one would actually be whatever that is. If this is 10 degrees, I could say that this is 170 degrees because I knew that that was 180. Go back 10. All right, now come over here and look at this triangle again, and let's just say, what is the sine of theta? That would be the opposite over hypotenuse. So sine theta is equal to y. Cos theta is equal to x. And tan theta is equal to y on x. Interestingly, sine is y and cos is x, so tan theta is actually the relationship of sine and cos. And that's a rule that you'll be using to do simplifications with later. Another rule that we'll be making a lot of use of is if sine is y and cos is x, I could put them into this rule here and say that the square of sine plus the square of cos is 1. I think I swapped the x and y around. That doesn't really matter, we're adding anyway. Also, just a quick note, if I say sine squared theta, I mean the sine of theta all squared. It's just mathematicians decided that this was easier to write. So there you go. So sine is the y value and cos is the x value. then I could go to my circle and I could say at this point here, whatever the y value is, will actually be the sine of that angle. Whatever the x value is would actually be the cos of that angle. So let's give that a go. Sorry, not the world's most awesome circle. Not too bad, I suppose. Let's take a theta. Now, if that's 90 degrees, I'll take this as a guess at being about 20 degrees. That's 20 degrees, and my circle was better. My x value would be pretty close to 1, but my y value looks like it's about 0.3. So I'm guessing 0.95 and 0.3 for my x and y values. Please work. Yay. So I'm going to go the sine of 20, which should be my y value. 0.34. I wasn't too far off. I'll do the cos of 20. 0.93. Oh, I was even better with cos. All right. And the tan. Now, I said the tan was 1x, but you can't really visualize that. So you can't visualize a fraction because if, you know, this is a bigger, you've got to divide, like that's a mess. So what we do for tan is we actually create a similar triangle. Make this triangle base 1. And if it's the same angle there, and it's still a right angle, it would be similar to that one. And I'll call the height of that t. So tan of this theta would also be t on 1. Now, if I wanted to represent that on my circle, I would have to make the base of my triangle 1 here and draw a... What is a line that touches a curve in one spot called? A tangent. I just drew a tangent. Guess where the word tan comes from? All right, so I've drawn a tangent. If I extended that line straight, that height there is going to be the tan of theta. So I'm expecting the tan of this 20 to be a little bit bigger than the sine of 20 was. So the sine was like 0.34. Let's try tan. I'm guessing, 0.39 or something like that. 0.36. Okay, not that different at all when those values are small. Let's do another one. By the way, when you're drawing the unit circle, so much easier to draw a circle then put the crosses in than it is to draw the crosses and then try and get a circle to sit on top. All right, let's pick a number up here, nice and big one. I'm going to guess this angle at about 70 degrees, 75 degrees maybe. Call it 70 degrees. That value looks like it's about 0.35, 0.3. And this one now is about my 0.95. If I look at my tangent value, woo, big. Okay, so the height at here is 1, the height at here is 2, the height at here is 3, maybe 4 off the page. Sorry, you couldn't see my finger, but I think that might join up at about 4, maybe higher. We'll see. Tan 70. Okay, 2.7. Fine, my angles are bad, I am guessing, but you do get the drift, right? You're getting the idea that I can guess this. Sine 70, 0.93, cos 70, 0.34. Now these ones I could predict already, because if you think about sine and cos of, I wanted a triangle here. If this was 70 degrees, this would be 20 degrees. So if the sine of 20 was this on this, that is the cos of 70. So when we had our 20-degree triangle sitting over here, it's exactly the same triangle. Yeah, it is. It's just rotated on its side. So the height of this is actually the base of this, and the height of this is the base of that. And so you can actually swap your sine and cos around, as you can see from the triangle, or you can see in the circle. So here's another rule that we're going to be playing with. The sine of 90 minus an angle is the same as cos of the angle. That comes in handy later on too. So why does all this matter? Let's just take a couple of exact value triangles. So if I have 60 degrees here, by Pythag that will be root 3. Therefore, I can easily find the sine, cos and tan of 60 or 30 by looking at this triangle. I'll keep that there for reference while I play with the circle. So if I take 60 degrees, now whenever I want to mark 60 degrees, I'm actually going to break this arc into thirds and come up to this one. That way I'll feel comfortable with where I'm putting my line. If you ever try and go, okay, a third out that way, it's harder to get it right. And you end up with these really weird squidgy looking, lines that aren't actually thirds or quarters. And we do a lot of thirds and quarters in these things, so worth noting. So there's my 60 degrees. So my sine of 60 degrees would be marking about there. My cos would be marking about there. Tan. Oh, needed a ruler. Tan's going to be up here somewhere. It's going to be above 1 but below 2. If I look at my triangle, I can see that the cos of 60 is actually 1 on 2. It's a half. If I look at the x value along here, I said cos was the x value, it's a half. I mean, I'll test it for you just to make a point. Cos 60, a half. It looks like a half. The other one doesn't look like a half. I do the sine of 60. That's equal to 0.86. That does look a lot better like 0.86 than it does like a half. And root 3 on 2 is the same thing. So it might be worth noting the decimals and learning these so that when you see them, you can remember how big they are. Not so that when you put sine of 60 in the calculator and you get 0.86, you go, oh yeah, that one's root 3 on 2, I don't have to do any work. I want you to do the work while you're studying this so that you actually understand where all this stuff comes from. And then down the track, when you're doing more complicated things, which will happen, it's maths, you know what you're doing. So please don't do shortcuts on this one, it's not worth it. All right, tan of 60 is root 3 on 1. Root 3 is 1.7. 1.7 was about where I think those two lines would meet at the height of this tangent. And so far it's working. The stretch that we make from basic triangles and heights and widths and things, which is everything we've known about trigonometry so far, is that now, because our theta, as I explained before, can go beyond 90 degrees, I could find the sine, cos and tan of this angle here. Now this angle I chose to be the direct reflection of this one, make that value there 60 degrees. So if that was 180, this one would be 120 if I subtracted them. So if I wanted the sine, cos and tan of 120 degrees, I'm no longer just looking at the base and width of this triangle, because that's the same as that triangle. I'm looking at the x, y, and tangent values. So if they're positive, they stay positive, and if they're negative, that's where they go. So we know that the sine of 60 is root 3 on 2, and the sine of this value is the y value for this point, which is also root 3 on 2. So the sine of 60 is root 3 on 2. Oh, 120 is also root 3 on 2. That's where I was actually trying to get to. The cos of 120 will be the x value, which is still looking like a half, halfway along, but it's negative a half. Because this was positive a half, it's exactly the same size, but it's on the other side. And the tan of 120, now this one's a bit weird for the tangent. What you have to do whenever you're in the quadrant that doesn't, you can't really join to this tangent by going this way. You have to actually come down. You have to follow the hypotenuse until you hit this line, and this line will always be on the left-hand side. Come down here. That's going to be the negative of the tan of 60, and the tan of 60 was root 3, so it's negative root 3. Yes, if I put it in my calculator, I go tan 120, and I get the ugly number. Negative, like I said, root 3 was 1.7, but this and this is y, and that's what's really important. What we've discovered so far is that if I have a basic angle, whatever my basic angle is in this quadrant, then if I put that same angle, same triangle in this quadrant and put that angle down there, then this angle here would be 180 minus that little guy. And the sine of that angle will be the same as the sine of this angle because they share a y value. Yet the cos of this angle is what I mean, is that value. The cos of alpha was this value, So they are negatives of each other. This is the negative cos of alpha. So sine 180 minus alpha equals sine alpha. Cos 180 minus alpha equals the negative of cos of whatever alpha was. The tan value also went the negative of the first one. Now, I've written the rules out here, but I don't really use the rules. I use the circle, and I look at the circle every time I want to know one of these things, because the rules are just another piece of algebra that you then have to plug numbers into and don't actually get any meaning from. And that whole thing of this, if you can embrace this and really grasp, work really hard at trying to get the meaning inside your head, all further trigonometry is easy. If you don't, if you resist, you'll suffer later. I've got no easy way of saying that. Okay. Here's alpha. This one, so in this quadrant, what we've noted is that the sine value was positive, but the cos and tan were negative of what went on in this quadrant. In this one, they were all positive. Come down here. And so this one, if that's 180 and that's alpha, this would be 180 plus alpha. In this one, the cos value, the x value is negative. The sine value is negative. But the tangent value to follow along that line is actually back to the original. If my circle was straight, that would be a straight line, same value. So in this one, the tan value becomes positive because I'm hitting the tangent up here, not because you're told t, okay? And then when I'm in this quadrant here, again, bad circle, naughty circle. The alpha here is alpha, but the angle is 360 minus alpha, or just negative alpha. They actually have the same value because they've got the same point on the circle. So 360 minus alpha is the same as the negative of alpha in terms of sine, cos and tan, because it's the same dot. Sine of that is negative. Tan of that, negative. Cos of that, positive. Now, in your textbook and in all the other learnings, they're going to go on about this all stations to central business or whatever phrase that they've come up with. And you've got to look in the quadrant, work out what quadrant is, work out what's positive or negative. If you do that without thinking about why, that's when I'm saying you'll suffer. So I'm going to leave you here in this video, and in the next couple videos I'll do a bunch of examples. And I'll give you a story to make it easy to remember.